In this video, I want to talk about inverses of linear transformations. But in order to do that, I really should start with inverses of functions in general, and also in particular, inverses of functions that you've seen before. Inverses of real valued functions that you've seen in calculus and in algebra. So just to go back to that kind of calculus algebra perspective, I've written down two functions here. F of x is x cubed plus 1, and g of x is the cube root of the quantity x minus 1. I've graphed both of these functions, and these two functions are inverses of each other. Now, when we talk about inverses in algebra and in calculus, I think the way that we present them is a fine way to look at them in that context, but is maybe misleading or even potentially wrong when we start to think of inverses more generally. So what do we mean when we say these two functions are inverses? Let's start with the visual picture. Visually, one way of thinking about this is that these two functions their graphs are reflected across this line that I've drawn in green, the line y equals x, right? If we reflect across this, the red function and the blue function match up with each other. That's one way to think about this. Another way that people often talk about this is more computational, which is something along the lines of we're switching x and y. And what people will often do is they'll, take this equation f of x and replace x with y and then solve for y, and then they get g of x. And that actually lines up with the graphical intuition. That is, when you reflect the entire coordinate system across this green dotted line, y equals x, you switch the x and y axes. And there's nothing inherently wrong with this perspective, but it doesn't make sense in a lot of contexts because switching x and y is only reasonable because x and y are both real numbers, right? That is, in other words, these are functions from the real numbers to the real numbers. As you move forward in math, you'll realize that, well, sometimes we want to have functions between different spaces. And we can have functions between different spaces that have inverses. And we can't just switch things around in formulas because a formula might make sense for a vector in R3, but that same formula might make no sense for a polynomial in P2, right? A quadratic polynomial. So we want to think of inverses in a slightly different way, but not in a way that makes all of this stuff wrong, in a way that when we reduce it to these real valued functions, lines up with all of our intuition there. And generally the idea of an inverse, so we'll get away from the graphs because we're not going to present this using graphs. In general, when we say that f and g are inverses, means that doing one and then doing the other gets you right back where you started. And so let's look at an example. So if we start with x equals 2, and we plug this into f, we get 9. And then if we plug this into g, let's be clear, this is f of 2, is 9. And then we plug this back into g. We plug 9 into g. What do we get? Well, we get the cube root of 8, which is 2. Or if we start with x equals negative 3, f of negative 3 is negative 26. And you can confirm that g of negative 26 is negative 3. So applying the functions in either direction on the same starting value and then applying one, then the other, we get back where we started. Or we could say this a different way. We could say that f of g of x is x. And actually, I showed two examples of applying in the same direction. I'm not sure why I made that choice. But if we go the other direction, we'll get the same thing. That is, if we first plug into f and then we plug into g, we'll get the same thing that we started with back. And you may have seen this as well. This is a common way of looking at inverses in calculus and in algebra as well. But this way of thinking of inverses will be a better way of thinking of inverses when we start to talk about inverses of linear transformations. So what types of functions have inverses? Functions that have inverses are functions that are bijections. So if we go back to our graphs, we can see that these two functions, I mean, at least on our picture, these look like they're bijections. So that is, if we draw horizontal lines through the graph, we always hit the red graph exactly once. If we draw horizontal lines again, we always hit the blue graph exactly once. And so these are bijections. We could verify that that's true. So what happens when we have bijections that are linear transformations? So let's look at an example. Here are two linear transformations, t and s, and you can guess, I mean, that these are going to be inverses of each other if you think about the last example, but let's show that that's true. So first of all, we could go and verify that these are both bijections. You can convert them to echelon form, and you'll see that you have exactly one pivot in each row and each column. How does this look in terms of inverses? Well, let's just choose an input. So let's start with the vector 1, minus 1. I'm going to apply t to the vector 1, minus 1. And when I do that, I'll get, well, I get 1 times 1 minus 1 times 3 minus 2. 1 times 2 minus 1 times 5 minus 3. And now I'm going to take that vector and plug it into S. And what will happen here? Well, minus 2 and 5 is minus 10, or positive 10. Negative 3 and 3 is negative 9, and so I get 1. And then negative 2 and 2 is negative 4. Negative 3 and negative 1 is positive 3, and so I get negative 1. So applying t then s, I get back where I started. I'll leave this to the viewer, but I'd encourage you to choose some vector from R2. Apply s, so multiply by b. Apply a, multiply by a. Or sorry, apply t, which is multiplication by a, and confirm that you actually do get back where you started. So t and s are inverses of each other. But we can look at this a different way. So what I really just did was I showed that if I first apply t to the vector 1, minus 1, and then apply s to the resulting vector, I get back where I started. But if I write this out, applying t is the same as multiplying by a. And applying s is the same as multiplying by b. And we've talked about the fact that matrix multiplication is associative. So what this is saying is that this is b times a times this vector 1, minus 1. And so I want to look at what is b times a. Well, B is -5, 2, 3, -1. And A is 1, 2, 3, 5. And when we multiply these out, we get the identity matrix. So there's a lot of things going on here, and I haven't really formalized a lot of what I'm talking about with linear transformations. And so I want to do that. I want to formalize a lot of this and then come back to these examples to understand exactly what's going on. All right, so let's talk about inverse linear transformation. So anytime we have a bijection, we have an inverse. Because if for each output value, there's exactly one input that goes to it, we can flip that map around and send things back. So if we have a linear map between two vector spaces, and we know it's a bijection, then it has an inverse. And inverse functions always go backwards. They take outputs and send them back to inputs. So they switch the domain and codomain. What's not obvious is that this inverse should have the same properties that the original function did. Because this is not always the case. In fact, if you go back to our example, I didn't even intend this, but I guess I chose this well. If you think calculus-wise, our original function is differentiable, that is x cubed plus 1, but our inverse function is not differentiable at x equals 1, right? It has a vertical tangent line. And so we generally don't expect inverses of functions to have the same properties as the original function. That's not something that we can assume is going to be true, but in the case of linear transformations, that is the case. If you have a linear transformation, that's a bijection, its inverse will also be a linear transformation. All right, so this is still kind of abstract land, right? Arbitrary vector spaces. So let's take this into the context of matrices. Well, if we have an n by n matrix, A, that is going to be, we can use that. Sorry, I should have written this differently. So let's So any matrix corresponds to a linear transformation, right? So T is the linear transformation corresponding to our matrix A, right? It's multiplication by A. So if we have an n by n matrix whose linear transformation from Rn to Rn gives us a bijection, then we can define the inverse of our matrix A just to be the matrix of T inverse, right? T is a bijection. It has an inverse, and it has an inverse that's a linear transformation, so that linear transformation has a matrix. And what we just saw in the previous example is not a coincidence. When we multiply a matrix times its inverse, we'll always get the identity matrix of the corresponding dimension. Right? That was what we saw here in one direction. Right? B and A are matrices whose linear transformations are inverses of each other. And when I multiplied these two matrices, what I got was the identity matrix of the right dimension. This is how the inverse of a matrix is defined. It's defined in this very abstract, seemingly roundabout way. Right? We're saying, look, inverses of functions make sense. Inverses of linear transformations make sense. When a linear transformation has an inverse, it's also a linear transformation. We have these matrices living alongside these linear transformations. This is how we define matrix inverses. So that's what it means to have an inverse of a matrix. We'll see in a later video, though, that we can actually figure out what inverses are in lots of nice ways. So we don't have to think of, when we're actually calculating inverses, we don't have to think about them as matrices corresponding to linear transformations. But this is the literal definition of the inverse of a matrix. It's the matrix of the inverse linear transformation. And these matrices have nice properties. And I'm only going to present two right here. One of them is just real quick. So the first property is that when we have two invertible matrices, if we multiply them, we'll get another invertible matrix. So an invertible matrix is just a matrix that corresponds to a bijection. It corresponds to an invertible linear transformation. And its inverse is going to be given by the inverses of the two matrices multiplied in the opposite order. This is not really even that hard to show, but I'm not going to. I just wanted to present this fact. So this is important. When we multiply invertible matrices, we get another invertible matrix. And the way we can see what that inverse is by multiplying the inverses in the opposite order. But the second thing is what I want to focus on. This is one of the real values of thinking about inverses of matrices. When we have an invertible matrix, then the corresponding system, AX equals B, where X is unknown and B is some given vector, this will always have a unique solution for all vectors in Rn. This is not new, right? So if A is invertible, that means that A corresponds to a bijection, and bijections always have solutions and unique solutions. So this is not what's new, but what's new is that we actually have a way of calculating what X is in terms of A inverse. The solution is whatever we get by multiplying A inverse times B. And I want to give an example of this. So I'm going to finish up the video by going back to the example we were using and just choosing some vector and showing that we can get a unique solution using this process. And so I'll write it down at the bottom, but recall that we're using the matrices A and B, and these things are inverses of each other. So this matrix B is A inverse. So let's say I want to solve the system. So here A is this matrix 1, 2, 3, 5. And let's say I choose, I don't know, 4 minus 2. And I want to solve AX equals B. This has a unique solution because A is invertible. How do I solve it? Well, I know, or I guess I'm telling you because I haven't really defined how to find matrix inverses, but this is A inverse. And so my solution to this is going to be given by X equals A inverse times B. Or in other words, here I get negative 20, negative 6, negative 26, 8, 2, 10. So X is negative 26, 10. And let's check. AX is 1, 2, 3, 5 times negative 26, 10. Negative 26, 30. That gives us 4. Negative 52, 50, that gives us negative 2. So this was actually a solution. And the value here is that if we know A inverse, I mean, we already knew how to, you might say, look, we already knew how to solve this system, right? We've been solving systems of equations since literally the first week of the course. You know, why do we need a new way to do it? This allows us to solve a system much faster. Right, we don't have to, especially think as our systems get a lot bigger, right? As we have more variables, more equations, we can solve this a lot quicker if we have an invertible matrix because we're just multiplying by the same matrix every time. In particular, if we want to do this a bunch, right? If we want to solve AX equals B for the same matrix A, but for a lot of different values B. And you can also hopefully envision that this would be really useful when you're working with computers, right? Because if I want to tell a computer how to solve a system, if I have a nice process for finding an inverse of a matrix, I can solve the system that way. So to finish off the video, just remember, coming up, we'll actually talk about, how do we do this? How do I, given this matrix A, how do I figure out that this is the inverse of A? We can confirm that it satisfies this property, which as it turns out is enough to force it to be the inverse, but how do we actually go about finding that? And so that's for a later video.